Hi. If you own a heat pump or you know how they work, you will probably not be stunned by the results of this demonstration we're going to do. Nevertheless, when you see the magnitude of the performance of a heat pump, I think you'll still be impressed. I was. For those of you who are unfamiliar with the way a heat pump works, it's really simple. If you own an air conditioner, you own a heat pump, albeit a unidirectional heat pump, which will pump heat out of a room and dump it outside. Really, the only significant difference between an air conditioner and a commercial heat pump is a couple of valves that allow them to reverse the direction of operation so you can move heat in either direction. Now you might think, why bother? If I want to cool off a room in the summer, use an air conditioner. If I want to warm a room in the winter, use a space heater. And you might feel confident with that decision because a resistance heater that turns electrical current into heat is about the most efficient mechanical device built by man. It's very, very close to 100% efficiency. However, a heat pump can be many times more efficient than this. Now you might be thinking, uh-oh, here we go, perpetual motion and free energy and over unity power generation. No, the operation of a heat pump does not depend on any of these fallacies. It does not break any thermodynamic laws. What allows it to work so efficiently is because it messes with entropy. Now, entropy can be a somewhat subtle and kind of complicated concept, but for the purposes of this video, we could pretty much exchange the word entropy at any point with equilibrium. For example, I have two beakers here filled with plastic beads. They're equally above the ground, so they're equal distant from the center of the earth, and they're equally filled. This represents the maximum entropy of this system. Now, if I take the beads here and I move them over to here, I've actually slightly reduced the entropy in the system, and it required a little bit of work to do that. I could conversely reverse the process and allow the beads to fall back into this beaker, increasing the equilibrium. And I could actually extract some power from that. If I had a little paddle wheel in here and the beads move the paddle wheel, we could actually extract a little bit of power. When you decrease entropy, decrease equilibrium, you have to add energy. When you increase entropy, you can extract energy. The nickels are interesting. If I do the same thing with these beakers full of nickels, these are heavy, and I pour them over here, I've decreased the entropy in this system. But the amount of energy necessary to move these nickels from one account to another is a lot less energy than earning the money to buy the nickels or power the space heater. The same applies to heat. Heat is kinetic energy, 1/2 mass times velocity squared. Now, because we're not doing nuclear fusion or fission here, the mass is a constant, it's a fixed. So if we add energy to a system, we're going to have to add velocity. And this applies whether or not you're using molecules in the air, you've got molecules in a cup of water, or you even have the particles, the atoms or the molecules in a solid crystal lattice. They vibrate more quickly as you add velocity. You're increasing the energy. Now, what's interesting is that because there is nothing at absolute zero, everything has some thermal energy, some movement. The amount of energy that is in even cold objects is significant. For example, if I took a volume of air at freezing conditions, 0 degrees Celsius, That has 90% of the thermal energy of that same volume of air in the middle of the summer. The difference between you freezing and sweating represents only 10% of the energy of the system. So all we're really doing with the heat pump is we're taking a system that may not be in equilibrium and we're adding a little bit more heat there at the expense of the other. That's why a heat pump can be so efficient. So enough talking, let's get to the demonstration. Now, imagine that this is your bedroom.
It's pretty nice.
At Starbase. What we've done here is I've placed the space heater over here and a fan blowing on the space heater to distribute the heat throughout this small room. The reason I've plugged both of them into a common cord that's going to end up going to a power meter outside of the room is because the fan itself generates a little bit of additional heat. The friction of the air and the inefficiency of the motor also contributes to the heating in the room. In addition to that, at the head of the bed, I've got a small thermal probe taped up here out of the flow of the air, measuring the general temperature inside of the room. This is test 1, and as you can see, we are prepared for test 2. So what I'm going to do is go ahead and close the door. And I've got this little wedge to keep it shut tightly. Good. Now, this is a power meter that reads in watts. This is a timer, and this is a temperature meter. There's two numbers here. One for T1, the top line here, represents a probe that we just have located in the hallway. The idea being that we just kind of want to keep track of this. There's no heat on in the building, there's no air conditioning in the building, but just to sort of reference what the general air temperature is in the building itself. The important number is the bottom number. It's reading 75.7. I'm doing this in Fahrenheit for you metric people. The only reason that I've selected Fahrenheit is because the units in Fahrenheit are smaller than in Celsius, so we get a little bit more resolution out of our monitor. So I'm going to go ahead and plug this in.
I can hear it going.
Yeah. And you can see that we're using about 1,368 watts. And we're going to start the timer. And we're going to let this run for about 30 minutes and see what kind of temperature we get to. We started at 75.7 degrees. All right, we're getting near 30 minutes here, and you can see that the temperature has gone up to, let's call it 85.9. So the temperature has increased almost exactly by 10 degrees over 30 minutes and 1,338 watts with the resistance heater inside of there. You'll notice in the beginning of the speed that we went through here, there might have been a little, the time lapse that we just did, that there might have been a period where this went blank. This thing, for power saving purposes, turns itself off after 10 or 15 minutes, so I had to turn that back on. But other than that, you can see, let's call it 86.0. be generous. Now I'm going to unplug this. This has gotten a little warm. And we'll stop the timer. And generously, we're going to say that's 86.0. So now what I'm going to do is I'm going to open up the room, take out the heaters, and we're going to leave the room open to the ambient conditions for about an hour and a half, about 3 times as long as the test, to let the temperatures equilibrate between the outside and the inside of the room, as well as any surfaces that might have even warmed up a little bit from the original heating. And then we're going to run the test again with this guy. All right, let's give that a little bit of time to cool. Ooh, it is warm in here.
Oh yeah, I don't like that.
Yeah, so much for Starbase, right? Texas? All right. Ooh, that's warm. Get these guys out of here. All right. And we won't need this guy either. Okay, see you in a few minutes. All right, we're down to 77 degrees. That's about as cold as we're going to get. We've waited about an hour and 15 minutes, so I think we've got a good starting point. Just to show you, I've removed the heater and the fan. The temperature probe is exactly where it was before, no change there. And now what we're going to do is I'm going to close this. Tightly. Then we'll plug this guy in. Good? No. There. Okay, timer's at 0. We're starting out a little bit warmer at 77. Let's call it 0.2, just to be conservative. So we're going to turn on the air conditioner now and start the timer. And then we're going to let this run for another 30 minutes. You can see that the amount of power being used is 350 watts. And that will increase slightly as it's working against a warmer room. It'll probably go up to around 400 watts, but we'll see that. And we're starting at 77. We're going to call it 0.2. And the air temperature in the hallway is almost exactly what it was before, 75.1 degrees. All right, see you in half an hour. All right, we're getting close to 30 minutes here, and you can see that the hallway temperature out here has actually dropped a few degrees. I'm standing in the cold blast right now. You can see that the temperature inside the room has now gone to 92.4 degrees. So it's gone up about 15 degrees versus 10 degrees with the resistance heater. And it's done that using 440 watts, so basically 1/3 the amount of electrical current. So it's about 4.5 times as efficient as the resistance heater. And this is not a very efficient air conditioner. This old unit is about half as efficient as modern window air conditioners that you can buy from a big box store today. So we're talking close to an order of magnitude more efficiency in heating compared to a resistance heater that's 100% efficient. Kind of neat, huh? Now, in the next video, we're going to show you how to improve the efficiency of air conditioners, and not by a small amount. It's estimated that approximately $200 billion a year is used worldwide to generate the electricity that drives air conditioning. So even a few percent reduction in the cost of running an air conditioner would make a huge difference and could save billions of dollars. And what we're going to show you isn't going to improve the efficiency by a small amount, but by a huge amount. So stay tuned. I want to thank you very much for watching. This is a pretty impressive result in my opinion. And if you're interested in what we're doing here and what we plan to do in the future, please take just a few seconds and subscribe to the channel. It really helps us to grow, and if you add a comment, that helps even more. And the bigger the channel gets, the more we can afford to bring you. Also, if you're willing to help support us on our Patreon, please take a look at the link at the bottom of the video, and that would also help us out a great deal. So this is a lot of fun. Hope you enjoyed it. You take care, stay safe, and we'll see you soon. Oh, 93.2 degrees. It's even hotter. I love this.